So in this video, we're going to introduce shear and bending moment diagrams. So we've been talking a lot about trusses, and trusses are useful for spanning a space. But now we're going to make a little bit of an abstraction and just talk about beams in general and not worry too much about what the internal structure is. So we have some sort of beam here. Internally, it could be a truss, or it could just be a solid steel I-beam, and we're spanning a space. So I have two supports here. And in this case, I just have a person standing in the middle. So the person just represents a load that we'll call P, acting downward in the middle. The shear and bending moment diagram is a way for us to understand the internal forces that have to be supported on the beam in order for it to stay in place. So the way we can see this is by imagining a free body diagram. So let me just draw a beam over here. And in this case, what I'm going to do is just draw a piece of it. So here's the same beam. But I'm going to imagine that I've come in with a saw and I've made a cut like right here or something like that. So now we've cut this beam and we imagine what are the forces that are acting at this joint that have to be acting right here in order for that beam to be held in equilibrium. Well, we know if the person is standing in the middle that the reaction forces at the edge here are quite simple. They're just P over 2 and P over 2. So when we draw the free body diagram of our cut beam, we have the reaction force P over 2. Now the question is, what are the forces that are acting right at this joint in order for the beam to be held in equilibrium? Well, since the sum of the forces have to be equal to 0, we have to have a force here acting downwards, and it has to be of a magnitude P over 2, so that the vertical forces are balanced. And this is what we call a shear force because it's the force of the two pieces sliding past each other. So imagine this is my beam, my two pins, right? There's nothing in the middle, so they just slide right past each other. Now if I took like sandpaper or something really sticky, I could probably hold a little bit of force if I push those together so they could support a little bit of shear. But when they're smooth, there's no shear. So that's what we call shear. Now it should be pretty obvious what the bending moment is now, because now I have these two forces which are not aligned, right? So they're acting on the beam like this, so the thing is going to rotate unless the beam can also support a bending moment. In this case, the beam wants to rotate in this direction, so we need to be applying a bending moment, which would cause a spin here. So I'll call that M. And the question is, what is the magnitude of that value M? Well, it depends on where we make the cut, right? So if I cut the beam anywhere between this support and where the person is standing, the shear force has always got to be P over 2. But the bending moment changes as we move from the support out towards the center, right? So at the support, if I made this cut right here, then my two forces are so close, the bending moment is basically 0. And as I move out further, the bending moment gets greater and greater and greater. Because remember, bending moment is force times distance. So if my coordinate system here is x, then my bending moment is quite simple. It's nothing more than P over 2 times x. And now I can see that something's going to happen when we pass this point. So let me draw another free body diagram. So here's another section of beam. And in this case, I'm going to draw it just a little bit longer. So I've still got my force P over 2 here. I've got my center force P acting downwards. And so sum of the forces equaling 0 means nothing more than now my shear force is going to switch direction. So it's going to be P over 2 upwards. My bending moment is going to change a little bit too, because there's going to be some sort of change when we go past this point. And if we work out what the bending moment has to be, well, we still have a contribution of P over 2 times x, right? This force times distance. But we have another one which is going in this direction, which is going to be in the negative direction, so I'll call that minus P times x minus L over 2, where L is just the length of the beam. So we should have written that in the beginning. So the length of my beam is L. So the center point is L over 2. So now we have a formula for the bending moment. Oh, and I've done that thing where I've kind of gone off the screen in the wrong direction. Sorry about that. And so now we have a formula for the bending moment as a function of x. So now it's useful for us to plot these two things. So let's draw two axes kind of right below our beam. One of these will be for the shear, and one will be for the bending moment. Now for some reason, shear force, we always give the symbol V, and the shear diagram is going to look pretty simple because it's just a constant with a change. So it's one value here, P over 2, it switches and becomes another value here. So that's x. So the shear diagram looks like that. So anywhere between the support and the person, we have P over 2. Anywhere between the support and the person, we also have P over 2, but it switches sign. And we'll talk about the sign in just a minute. Now the bending moment is going to be a linear function of x. So when x is equal to 0, the moment is 0. In the middle, it's going to be PL over 4, because x will be L over 2. And so that means we're going to have nothing more than a linear increase of the bending moment here. Now, once we reach the middle, this function is going to change a little bit. So let me rewrite this formula here. I can rewrite it as P over 2 times L minus x. So if we just rearrange this formula here, we get that, which means now the slope is the same but negative. When x is equal to L, the moment is 0. So I'm just going to have a straight line that goes back down. So now you've created your first shear and bending moment diagram. And this will be useful when we look at truss structures because it helps us understand all the members and which ones are in tension, which ones are in compression, and why we see this kind of alternating tension and compression for the diagonal members in the center. Before we do another diagram though, let's talk a little bit about the sign convention. So in most textbooks, what you'll see is if I imagine a cut element of the beam from the center, so I've kind of removed it from both the left and the right. So there's some piece of the beam here, some piece of the beam here, and we're just looking at a section in the middle. The sign convention for positive shear would be that, and the sign convention for positive moment would typically be that. Now it's kind of arbitrary, it doesn't really matter. We could pick one or the other. We could flip this around and our diagram would just be, we could flip this around and our diagram would be just as accurate, but we have to pick a sign convention. So this is the one you'll find in most textbooks. So if we work from the left like we did in the last one, the downward shear is what we call positive, and the moment, which is turning this way, is upwards. So the way I always remember the moment is because if you imagine the moment, what it wants to do to the beam when it's positive is bend it upwards. And since it's positive, it's like a little happy face, right? So it wants to bend it upwards to smile. So let's draw our beam here. We're going to do very similar to the last one. Except rather than having point load, we're going to have three loads, P, P, and P. And that means we're going to have an upwards reaction force here at the two ends of 1.5 P and 1.5 P. Okay, so now we want to draw the shear and bending moment diagram for this. So let's start with the shear. So I think we can kind of do this one by inspection, at least the shear diagram, though you should of course work through this yourself and make sure you agree with me. If you imagine making any cut here, right, anywhere between here and here, it's pretty obvious that we have to have a downward shear force of 1.5 P. So up to this point here, we have 1.5 P. Once we cross this point here, now my free body diagram, sum of the forces in the vertical direction, I've got 1.5 up, I've got 1 unit down, so that means I've got 0.5 up that I need to counterbalance. So this drops down to something like that, and then we have 0.5 P. Once I pass through this point, now the shear force has to be upwards because I have 1.5 up but 2 down. So now we jump something like that. And then finally, I think it's, you probably see the trend now. If we come here, the shear force has to be 1.5 again. So my shear diagram has this kind of stair-step shape that looks like that. Perfect. So now the question is, what does the moment do? So the moment's perhaps a little bit more complicated, and the first time you do this, you probably have to be a little bit more systematic about it. But let's see if we can kind of construct it as we go along, and then of course you should check the result yourself, because the only way you learn to do these things is by doing them yourself. If you just watch me, you'll never get it. Okay, so there's our moment diagram as a function of x. So if we look at the last one, by analogy, we should be able to do that, right? Because if I look at just this first little section of the beam here, I've got 1.5 P going up, I've got 1.5 P going down. So this is the section right here at the very beginning. Again, this thing wants to spin that way, so we have to have the counteracting moment going in our positive direction, making the beam want to smile, bend upwards, which has to simply be 1.5 P times x. So we're just going to have kind of a slope here up to this point. Right? By symmetry, you can kind of see that the other side is going to be the same. Right? So if I go from this side, I also going to have 1.5 P going up. So we can just solve this one kind of by symmetry. Now the question is, well, what happens here in the middle? Well, we can do that by just simply constructing our free body diagram. And it's kind of the same as we had in the last one. We just need to be a little bit careful. So we have 1.5 P going that way. We have P going down, right? So I'm just drawing up to this point here. So that means our shear force, like we said, is going to be downwards of 0.5 P. And then we have some moment twisting the beam in that direction. Now we can work out what this is. It's quite simple. We have two contributions to the moment. One is 1.5 P times the distance from the end of the beam. I'll just call that x, right? So from here to here, right? That force exerts a moment. And then we have minus this component of the thing, which is this component P, and the distance is nothing more than x minus L over 4. So again, for some reason in every example today, I keep forgetting to draw the dimension of the beam. It's of length L, so if these are equally spaced, that's L over 4. L over 4, L over 2, 3/4 L. So we have a formula like that. So what that means is now the slope is reduced because I have a slope of 1.5 here, but I take one off, so now my slope is positive, but it's 0.5. And so what that means is there's still going to be a little bit of slope here, but it's going to be, you know, kind of a bit shallower. And by symmetry, it needs to meet in the middle. So our diagram is going to look something like that. So two kind of straight line segments where this one is shallower than this one. All right, perfect. Okay, so now let's do another example. In this case, I'm going to have a distributed load that I'm going to call Q. And what that means is this is really a force or a weight per unit length. So if you imagine a beam under its own weight, it's not a bunch of point loads, but it's a certain amount of mass per unit length with gravity pulling it downwards. So we're going to call Q a distributed load that's just given in units of force per unit length. Since this beam, the length is generic, is L, the total downward force, the total force, and the total load of this beam is nothing more than Q times L. So that means our reaction force in this case is quite simple because everything is nice and symmetric. This is just QL over 2, and this is QL over 2. So now let's see what the shear and bending moment diagram for a beam under its own weight is. So let's draw two diagrams down here. So this will be our shear, V. This will be our bending moment, as usual, M. And this is our coordinate direction, X, which is the distance from the end of the beam. Okay, so now let's just isolate a little free body diagram over here of an arbitrary section of our beam. So again, all I'm doing here is taking my imaginary chainsaw, slicing the beam here, and asking the question, what are the forces that are holding this thing together internal? So I have a point load here at the reaction, QL over 2. I have my distributed load like this. This is my dimension X. So what does that mean? Well, it means I need to have a shear force, which looks like in this example will be downwards, at least as we're close to this edge. The magnitude of that thing needs to be QL over 2, so it needs to balance that, minus the equivalent load of this piece, QX. So there we go. So our shear force is going to be QL over 2 minus QX. So what does that mean? Well, when X is equal to 0, we've got a shear force of QL over 2. When X is equal to L, at this end of the beam, we have minus QL over 2. And so what do we have in between those 2 points? Nothing more than a line. So there's our shear diagram. And so now you remember when we had a point load in the center, it was a constant, then a constant. Now we just have a line, a continuous change in shear from one end to the other, with 0 in the middle. Okay, now what's the moment? Well, the way we can figure out the moment is, if we think about it, this piece here, this distributed load, is equivalent in terms of a moment of a force with a magnitude Qx acting at its centroid, so at a location x over 2. So those are the two contributions to the moment then. So the moment, which is going to start off at least for sure, in this direction we can see if it changes. So the moment needs to equal to QL over 2, so that force, times distance, which is x, minus Qx times the distance, x over 2. All right, so now we've got it. So if we put this together, we see now we have a quadratic term here, right? Because it's Qx squared over 2 QL over x. The other way I could write this that might be more convenient is Q over 2x times L minus x. And so what that's going to mean is when x is equal to 0, the moment is 0. When x is equal to L, the moment is 0. When x is equal to L over 2, the moment is a maximum and will be positive, right? Because L minus L over 2 is a positive number, and in between it's just going to be a parabola. So we have something like that. Kind of a poorly drawn parabola, but I think you get the idea. All right, one final example and then we'll be done. So as our final example, let's do a cantilever beam where we have a beam attached rigidly to a wall. So in this case, it should seem obvious that the wall needs to exert a reaction force upward, which needs to counterbalance the load P in order for our sum of the forces to be a 0 in the vertical direction. But you can also see that the wall needs to apply a moment. So again, this is like a beam attached rigidly to the wall. So in order for me to hold this in place, I have to apply a moment with my right hand here, right? in order to keep that in place. So in this case, the beam wants to rotate this direction. So we need to add a counteracting moment acting in that direction. So now in order to draw our shear and bending moment diagram, we should be able to do this quite easily, because all we're going to do is imagine that we cut the beam here and ask what are the forces that are holding the beam together. So it should seem pretty clear that we need an upward force here, P, and that force is going to be the same all along here. So the shear force is going to be upwards and with a magnitude P, and so using our sign convention, that will be negative. Our bending moment internal to the beam is also going to have to be similar to what we have here, and it's just going to have to be counteracting in that direction, and it's going to be nothing more than P times X, so the distance from the end. So it's going to start at 0 and end at P over L. And now the beam is bending that way, so it will be negative. So all that means we have a pretty easy diagram to draw here. So again, this coordinate is X, this coordinate is X, this is the shear, this is the moment. Our shear diagram is just a negative P constant minus P, and our bending moment will start at 0, right? And it will go with a slope downwards because I've drawn it in the negative direction by our sign convention. And it ends so that it has a magnitude of P times L. Okay, so you'll have to do a few of these yourself to get practice doing them. And in the next few lectures, we'll look at how these diagrams relate to the internal forces in some of our truss structures and how it can help us understand things a little bit better.